Okay, so we're in chapter 8. We're still looking at theories of the origin of the solar system. None of us were there to figure it out. So we're piecing together all of the data and the observations that we've made. We've looked at solar nebula theory. We have looked also at condensation theory. And we're comparing those to characteristics that we have observed, and they're doing pretty well. But we haven't found one theory that addresses anything, and I doubt that we will. But let's go to another theory that might address our characteristics of rings in the outer planets, the Jovian planets. The theory is called the planet building theory. It has two models or two hypotheses underneath it that still are accumulating data. And the one is the accretion model, and that's for the inner terrestrial planets. The other is the disk instability model, and that is for the Jovian planets. So let's go into it because it could explain the rings on the Jovian planets, and it could explain the space debris that we know in our solar system. Now, here is a slide about the two planet formation models in this theory. The one, as I said, is called an accretion model, and it really talks about the planetesimals, and it talks about the dust forming the inner planets, the terrestrial planets. And the gas collapse model, which is also the one you saw back there. I'm just going to go back here. The disk instability model is also called the gas collapse model. That really talks about the protoplanetary disk from the solar nebula theory and the dust that's forming throughout the entire disk. So in other words, we're still working on solar nebula theory. We're adding on condensation sequence theory. Now we're adding on these theories of planet building. Here's the thing. We're going to be talking about the accretion model for the inner planets first, a slow accretion model. Remember I told you it would take millions of years to get to 1 or 2 centimeters for a planetesimal. This gas collapse model is actually a very rapid collapse. So these two models don't go together so well. Just letting you know that from the very start. But let's start with the accretion model. And what it says is that the planetesimals contain both rock and metal, as they do on the inner planets, and that the planet grows by accretion of these dust particles. Now, these dust particles grow and stick to each other because of some really low velocity collisions. So it's not dramatic collisions at all, because then they would bounce off of each other. These are low velocity sticking collisions. And what happens in this is the planetesimals grow from a few centimeters to a few meters, and then they start to get some mass to them while they are accelerating in this counterclockwise rotation. So they have gravity, and they can start to grow and attract other bits of metal to them by gravity. So they start to grow bigger. Now, the biggest protoplanets that happen to form can grow faster gravitationally. And this model also extends out to a bit of the Jovian planets and the gas. Because if you had a bigger protoplanet that instead of maybe a few centimeters, maybe it was a few meters, it could start to capture gas when it is to the point when it is about 10 Earth diameters. Then it can start to capture gas gravitationally. But guess what? The planets that are in the terrestrial area, the inner area, never get to be that size. So they never get to capture that gas, and they never grow that big and that quickly. Now, on the other hand, because they don't capture the gas and a lot of the um, debris as quickly, that debris tends to hang out in the terrestrial area as possibly the asteroid belt that is between Mars and Jupiter. So here we have a model of accretion that might explain the asteroid belt a bit, but it really can explain the ring systems that you might notice in the solar system, because if you had a protoplanet that was larger than 10 Earth diameters, then that large mass can start to take in a lot of dust and a lot of gas, and it can start to take in a lot of ring particles. So that this large mass model, this accretion model, can explain the ring models a bit. And it can explain the fact that there are clouds of dust and belts of dust past the Jovian planets, because it can explain that as the sun lit up, the solar wind of the sun could blow all the rest of the dust past the Jovian planets. So there is some thought that the accretion model can look at the rings and can look at the Kuiper belt and the Oort cloud of dust beyond the Jovian planets. Now, we still haven't talked about the disk instability model, which really concentrates on the Jovian planets, the farther out planets. This model also relies on the disk theory from solar nebula, and it relies on the condensation theory from going from dust particle to a clump of gas. So this disk instability model talks about a gravitational disk that develops clumps of gas based on this dust that's condensing, and those clumps of gas tend to destabilize the disk, so that the theory goes that the dust grains can coagulate and they can form a planet with a core. And that planet could go on to sweep out areas and sweep dust toward it. Let's go into this in some detail here. About this clump of gas that's forming. Remember, we've got some condensation, right? We've got our protoplanetary disk and dust and condensing there. Dust upon dust upon dust forms clumps of gas that destabilize this very gentle disk that we've got, a protoplanetary disk, and start to break them apart into planetesimal areas that can form their own cores. So this is talking about a clump of gas rather than the rock and metal. The disk instability model is definitely all Jovian. There's no rock or metal in this. So this is definitely a Jovian model that talks about the fact that these planetesimals that are full of gas are sweeping out all the debris around it and sweeping out that area, which makes a lot of sense if you are looking for bands that don't have a lot of debris and bands that do have a lot of debris. You would sector out the debris into areas where there would be an asteroid belt in front of Jupiter, but Jupiter sweeps out its area pretty clean in the Jovian planets. And then you'd have the Kuiper belt after the Jovian planets that have all been swept clean, and the Oort cloud even beyond that with the leftovers. So now we've got these two models that have explained rings and have explained a bit about the debris. But we still got some problems here. We've got some problems with the solar nebula and some problems with the condensation theories and even with the rock building theories. The planet building theories. And if we go down our characteristics, we've got problems in planetary types, in space debris, and in common age. Let's go over a little bit the planetary type problems. First of all, if we're talking about these theories, we are basically looking at the size of planets that start small around Mercury and then go huge around Jupiter and Saturn. You would think of progressively larger from the sun. That's not really what happens. Mars is too small. It's smaller than Earth, and it's farther out than Earth. And Uranus and Neptune are smaller than Saturn and Jupiter. It doesn't seem to make sense. The theories don't hold for that. Nothing explains the size of our moon, which is too big for us to capture with our gravity. So that's another conundrum. Nothing explains the Venus counterclockwise rotation in what we've heard about for the theories so far. Nothing explains Uranus in that very strange axis that it's on. It practically keels over at 85 degrees. We have to think about some of these oddities here, along with the very strange and elliptical orbits in the Kuiper belt and in the Oort cloud, and this timeline problem, which I told you was going to become a problem. The accretion is very slow. The gas collapse is very fast. They don't go together for a common age. So fortunately, we have some more theories that can explain some of the problems that we had with the planetary types and the fact that the sizes don't match up. Maybe we should be talking about catastrophic theories. What's catastrophic theory? Catastrophic theory says that there are some violent events that just cause differences that require us to pay attention to them. If our moon couldn't happen by a gravitational capture by our Earth, then it could happen by a collision that pushes our moon off of the Earth's protoplanetary sphere. And collisions could also account for the counterclockwise rotation of Venus and could also account for Uranus's very strange axis. But collisions don't talk about the size of the planets and the fact that Mars is smaller than Earth and Uranus and Neptune are smaller than Saturn and Jupiter. But fortunately, we have another theory, and that other theory is planet migration theory. And we are going to be talking about that for explaining the differences in size, the differences in the space debris, and where it's at. And it can also explain some of that common age problem that we've got between accretion and between gas collapse. And that will be on the next video.